has to maintain the same force with respect to the system. Otherwise, this thing is going to move too fast. That you have to counteract the force.
If the piston had a mass,
Yes,
but there were no spring,
there's no spring, correct, yes,
it would still move slowly, but it would move.
Yes, it would move,
It would
correct.
move forever.
It will move forever. Yes, right. So the whole thing has to be done quasi-statically.
Can you think of quasi-static as like, it's expanding slow enough that pressure is the same all the way throughout the gas?
Yes. Basically, we want to make sure that quasi-static, in this case, in practice, means that they have a system, right? So processes has to happen so slowly that at every single point in time, the system is in microscopic, almost in microscopic equilibrium. Right? So you can define pressure everywhere, right? And things like that. Yes.
What I'm kind of confused about is
Or temperature should change across the system.
what I'm kind of confused about is that something's if a process is quasi-static, right? Then you just said it's going so slowly that it's pretty much in equilibrium, right? Isn't that the
yes,
same thing as it being reversible? Like if it's going so slowly that it's in equilibrium at each point, isn't that what reversibility is?
Good point. I don't know how to explain this properly. Just give an example. No, not necessarily the case. The example that is the clearest is the one I gave yesterday. If I have two systems, finite temperature difference, D1 and D2, right? Okay? And if I put them in thermal contacts here, right? If they're in thermal contacts, they can exchange, if D1 is greater than D2, right? And they can exchange heat, right? This is not reversible or non-quasi-static. Also, right, if things are happening too fast, right? If this is high temperature, this is low temperature, you have a lot of heat transfer, there's disturbances, right? But if I put an insulating material so that heat transfer very slowly, right? Then the whole thing is quasi-static. Right? So if this is almost semi-adiabatic or semi-insulating, right? And this dQ is small, right? So at every single instance in time, the temperature across here is always uniform, right?
Okay, but so the thing that keeps it from being reversible in this case is the fact that there is a finite temperature difference?
Yes, okay. Because of the finite temperature difference though, right? Because this is T1, T2, and T1 is equal to T2 plus some finite number, right? Not differential. Heat can only move in that direction. Heat can never move in this direction. Right? The only way that heat can move back and forth is that if this is T and this is all T. Let's do it again here. The only way that heat can move back and forth, right, is when this is T and this is also T. Right? If I just raise it a little bit by dt, heat will flow that way. I lower it a little bit by dt, then it will flow this way. Right? It's reversible. But this one is not, because this one is a delta difference. If I raise this by dt, it still go that way. And if I lower by dt, it also still go that way because of the big delta. Right?
Okay.
Yeah. This is something that you have to be clear about.
What do you mean by the delta? It's just, it starts off at different.
Yes, it starts off at a big different temperature. So this is 100 degrees Celsius, and this is say 80 degrees Celsius, something like that.
But what if it reaches the same temperature after equilibrium and then you just do DT?
Oh yes.
And then it
Once they become the same temperature, then yes, reversible.
Okay, so it's just in the initial case.
Yes.
it won't go
Correct. Mm-hmm. Right. So things can be quasi-static, but not reversible.
I see.
Yes.
So in this case, like if you wanted to make the process reversible,
Mhm.
like if you want to make all the heat from T2 go to T1, then you could
Yes.
just make it like the limiting process of like extremely small DTs. But
Uh-huh.
in that case, you wouldn't necessarily need a like insulating thing, right?
Wait, in which case here? I'm confused. In this case?
Like if you wanted to make it reversible,
Uh-huh.
then you would just go really, you would like make the temperature difference really small, right?
Right. Or no, in fact, it has just have to be the same, almost.
Oh,
you know,
okay.
because for things to be quasi-static, you have to be able to change things by differential amount, right? But if there is a finite temperature difference, right, differential change in temperature will not lead to a process to go back and forth,
Oh, okay.
right? Because of the big delta. Right? You see?
Clarification on something. Being reversible is a consequence of being quasi-static, right?
No, not necessarily. That's the whole thing. Yes, yeah. The requirement is not sufficient to be quasi-static. I mean, it's necessary to be quasi-static for things to be reversible. Okay. This is, it takes time. I mean, it's, probably in the end doesn't really matter for problem solving, right? But most of the problem that you have would be reversible problem. Yes.
I have a question, but it's not from yesterday, it's from 2 days ago.
Yeah.
But I think we were matched up in the textbook, because I think we're using different,
Okay.
we're using a little bit differently. So in your lecture, you told us that C sub V is 3/2 NK, but then in the textbook it said, was it C sub P minus C sub V is R? And your
Right.
lecture was NK
Yes,
sub V,
yes,
so
yes.
is it different units?
Right, it's a different unit, different,
Okay.
different.
Because in the textbook it was calories per mole Kelvin,
Yes,
and
yes.
we use calories per Kelvin.
Different unit and different. I always use an extensive variable in the discussion. They use an intensive variable, right? So we should clarify. Did I answer all your questions about the quasi-static and reversibility? Just want to finish that discussion. Right. So, I mean, it's really important for an understanding of chapter 20, right? As you will see tomorrow. I mean, I'm not interested, as I mentioned to I think Patrick yesterday. We're not so interested in trying to find efficiency of engine, right? Because all engines are just not reversible. Right? But the insight of Carnot is actually to use this concept of reversible engine to understand thermodynamic processes. Right? And that's what we're going to do. Right? Right? It's not about finding efficiency of engine. That's why I'm not going to talk about autocycle and all that. Right?
Just to clarify, the first case, it's still quasi-static but not reversible.
The first case,
The left side.
yeah, if it's finite difference, right? If T1 is equal to T2 plus finite
Yeah, and
differential.
quasi-static because it's going very slowly.
Yeah.
So, okay.
Yeah, you can make sure that this process happens very slowly by putting an insulating material in between it, right?
Mhm.
Right, it's
But it's not
quasi-static,
going to go the other way.
but it's never going to go the other way. Yeah. Okay.
I have one question about
Yes.
like when you say like slow enough, is that how? Because I know steam engines are really fast.
Right. Yeah. This is all just like back to 7A when you have frictionless cable and massless pulley, yeah, right.
So slow enough just means not super fast.
Yeah.
But if it's pretty fast, it's still quite static.
Right. So you, in the end, as Iman was talking about on Friday romantic, it's all a matter of time scale, right? So if two processes, one has a very fast time scale and the other one has a very slow time scale, then from a consideration of one of them is always stationary. You see what I'm saying?
Yeah.
It's all a question of time scale. So if I have I don't have a good example right now.
I mean, it looks almost like, the definition of slow enough is just differentially slow.
Yes.
Like the change to the system that's occurring is happening you can define it for differential units of temperature. pressure,
Yes, mathematically you can do that, but if you want to compare to real experimental practice, right, then you usually have many time scale, right? It's like a coffee boiling at the table, right? You have many time scale, right? There's a process of evaporation, And there is a process of video reduction, and if one of them is much faster than the other, then you can consider it to be quasi-static for one of the processes. Okay. Did I answer your question? I hope I did. Okay. So back to your question. This is important. So ideal gas, Cp minus Cv is equal to mk. Right? And this is actually heat capacity, right? But nobody calls it heat capacity. So this is extensive, big C. It doesn't help that big C and small c look the same. So this is actually extensive additive. So it's proportional to n, right? And the specific heat is intensive. Right? So it's independent of n. Now there are also a question of unit, right? Chemists write it as NR. NR is the same as NT. This is the number of mole, right? So N is just the number of, is N divided by the Avogadro's number. What is the Is N divided by 6.02 times 10 to the 23. And then R is then just NA, N Avogadro times KV. Okay. So, but then when we talk about heat capacity, when we talk about specific heat, sometimes it's quoted, especially in chemistry book, it's always per unit something, right? Per unit mole usually. But it can also be per unit mass, then you have to do all the conversion. I'm too lazy to do that. But we could do it if you want. Right? So the specific heat then, in this case, if it's per unit mole, then it's a small c, right? Then Cp minus Cv is just, since we're doing mole, is n R over n, which is equal to 4.
Yeah, I think in the textbook, they had small c and large c too, but then they used large c for molar and small c for mass. So that was even more complicated.
Okay.
And then yours is by number density?
Yes. And then there is in my lecture I said that all my density for thermodynamics will be number density.
Yeah. Okay.
And so these are all just personal preferences, right? When I make my test, I will stick to my personal
So
preferences.
real quickly, could you give me the units for CP?
Sorry?
Could you give me the units for CP?
This one here. So for ideal gas, say let me see. For ideal gas, for monoatomic, say, then Cv, big one, right? How do you say big? Big Cv is 3.5 mK, right? And then so if you write it the way chemists write it, right? I'm not trying to do that chemists, actually. I wish I was doing chemists. Don't. It's 3.5 R. Right? Oh, no, I'm wrong, yeah, and R, right? Right, because extensive, right? But the intensive variable, Cv, is 3.5 K, and this is the chemist write it as 3.5 R. Right?
Do you mean like?
But this is specific heat, this is basically heat capacity per unit mole. Per mole. Right?
Would that be like per atom or something, or per molecule because it's just K?
Yeah, this is just per molecule in this case. But this is, no, yeah, it doesn't really translate, right? Does it translate? It doesn't necessarily translate, yeah, because here I'm dividing by the total number of particles. Here I'm dividing by the mole. But you get the idea, though. The necessary understanding of this is basically I'm saying that every degrees of freedom get 3/2 K specific heat, right? Okay. It will be clear from the problem. When you're given a problem, it will be very clear that you should use this, that, or this, or that, right? You're right, this is not exactly the same as that, right? Because this is for mole, right? This is for particle.
Well, we have to know, be able to figure out how many degrees of freedom each, like say, a certain molecule has.
No, that's actually not very simple, right? Yeah, so you will be given that number, like in all the problems that you have in the textbook, they talk about. So monatomic, you have 3 degrees of freedom per particle, so 3n. Right? Just to complete this, right? Let me just complete this for now. So take Cp, then it's just Cp plus 3/2 Nk, it's become 5/2 Nk. With the chemistry unit, it's just 5/2 R and R. Okay. So this is always true. This statement that Cp minus Cp is Nk is always true for ideal gas. Right. Now the question is finding Cp. And Cp depends on the degrees of freedom. Right. And for monatomic it's always 3n, 3 per particle. But for the atomic, they always give it to you as 5. It's not really 6. And that is actually not as obvious. Right? I mean, in theory, if you have as I was talking about this yesterday, lectures, if I have a diatomic molecule, say, it's like a molecule, a younger molecule, right? Not helium. Helium is monatomic, but hydrogen, oxygen, nitrogen. What else? Or other way, hydrogen chloride. Okay.
So it doesn't matter the type of bond or the actual molecule, it's only how many there are?
Well, if you're just counting, yes, if you're just counting, you would think that there's 3 here, you should have 6. Right. It turns out it matters what material you have, because it turns out, this is discussed in the book, that you should read it. I was hoping to actually cover it in class. Maybe I still will. What happened is, in reality, right? So, just classically, thinking classically, you think, well, there is a Cp has to be, because there's 6 degrees of freedom, then this becomes 6/2, and right? That's what you expect, right? But in reality, this thing is actually as a function of temperature. So for you should read this in the book. It's actually not a bad discussion. I like to do it with Giancoli, but it's actually not that the way he described it. So this is, transition temperature 1, T1, T2, this is molecule specific, right? But at some point, this is actually 3/2 Nk. For the atomic, this is the atomic. And then as the temperature is high enough, the specific heat is flat. This is actually flat, by the way, right?
Because it's like
This is 5/2 Nk.
So do you go just by like whole number, like 3/2, 5/2, 7/2, 9/2?
No, in fact, it's a bit more complicated than that, actually. It's to solve this completely, it's actually quantum mechanical. So if you have a it's a very good question, though. If you have a triatomic molecule, right? Does it step by Nk? No, it's not. It's not like that. Yeah. So it turns out there's also 7/2 here. And this is beyond the scope of this class. Right? So there was never 6.5. There was never 6.5. Right? And then the 5 comes from the fact of this dumbbell, right? So I can consider this as the center of mass, by the way.
Oh, I was going to actually ask about that.
Yes, right. So if I have a atomic molecule, right, I can look at the center of mass. The center of mass has 3 degrees of freedom, right? And then for rotation, I can rotate around this axis, right? This is x-axis. Let's call this y-axis and z-axis, right? And I can also rotate around the z-axis, right? Rotation around x, rotation around y. Right, there's 1 degree of freedom, this is another one, right? But you should also be able to rotate around y, right? In theory, if this is just a finite dumbbell, right? If you're a dumbbell, right? You can also rotate around the axis of the dumbbell. That's rotation around z, right? But that's not allowed.
I think Z and Y.
Oh, sorry, yeah. Sorry, z. This is y. Okay, so rotation around y is not allowed actually. But that's a quantum mechanical reason. Right? But what happens, so that's why you have on the 5. 3 from the center of mass motion, and another 2 from rotation.
So then was the argument in the book about like the moment around that, is that like not a correct?
Yeah, well, that's like the justification after the fact, right? Because you know what happened in reality. People realized that the reason people realized classical physics was completely wrong is it started with Planck, right, with black body radiation. That's not true at all. Maxwell already knew about this 50 years before, 1855 or 1860. He knew that it has to be 6.5. Classical calculation will give you 6.5. So that thing that was discussed in Giancoli is wrong, right? That justification won't work because it has no moment, you know, but it's not a classical argument. Right. It's justification after the fact. Maxwell thought it has to be 6.5. But then this is all done in 1800, right? He knew this. And there was a statement in his paper, this is a big problem. This is why thermodynamics is probably stay wrong. Right? So this is like 40 years before, just a little historical aside. Right? So yeah, classically it has to be 6.5. Okay, but in your problem, you know, as you know, in the homework they always tell you, well, let's consider 5 degrees of freedom, right? They always give it to you. Right, so I'll give it to you. Well, let's say there's 7. Right. I haven't even started. Any questions so far? Yes.
Unrelated question.
Yes, definitely.
So
This is your time.
Okay, so I noticed in the book, like, on section 19 for adiabatic expansion, it says that the change in internal energy is equal to, like, n times specific heat for volume times change in temperature.
Yes, correct.
So, like, that didn't really make sense to me because they derived it in terms of, like, an isovolumetric process where there's work done.
I'm probably confused a little bit, but what you said, EM, but it's an adiabatic process, right?
Yeah.
It goes from point A to point B again, right? P, M, equal constant. Right, so this is point 1, point 2.
Yeah.
But energy is a state function. Right? So if I want to know the energy difference, right, if I want to know delta U, it's just going to be U2 minus U1.
Yeah.
Right? And then for ideal gas, you know, U is equal to, it will be given, you know, whether it's a diatomic or monatomic, right? You have NK. Right? So if you know the temperature at that point 2, so this is just when we have NK E2 minus we have NK E1. Right? So when things are, when a variable is a state function, usually it's a lot easier, but you don't have to integrate, right? You just find the value at one point, you subtract from the value from another point, right?
What the book did was that it said like for an isovolumetric process,
It's a volumetric
you're
process.
not doing any work, right?
Yes, no
So
work.
then the change in energy is equal to the change in heat.
Yes,
And then
yes.
the change in heat is equal to like
Yeah.
N CV times T.
I think it's a roundabout way of explaining it, yeah.
Which is okay, that's like a
No,
definition.
you're right, you don't like it, I don't like it either.
Also it says, yeah, so it says that's for an
I mean-
yeah.
Right, you know how it is in thermodynamics, right? You can go around in circles, right? You know, like that,
Yeah.
because of how you define things, right? No, I mean, the book will give you the right answer, but I think the reasoning is a bit iffy,
Okay.
right? But, you know, it's correct, it's not wrong. Yes, okay. Other question, there was another question.
Yeah. Do T1 and T2 correspond to anything physical?
Oh yeah, this will depend on the type of diatomic molecule that you have, and this can be calculated, but it will be, you know, with one mechanical calculation.
But those aren't phase transitions, right?
No, it's not a phase transition. Oh well, no, it's not a phase transition. You're right. That's a good question. It's not a phase transition.
If for only gases, right?
This is gases. Yes.
Shouldn't T be fertilizers?
No, specifically. I mean, if it's monatomic, right, as a function of temperature, I'm just trying to write this as a function of temperature, right? 5 CV, for monatomic is always 3½ MQ. Okay? But for the diatomic, it goes into plateau, and the step function. Right? And along the plateau is flat.
But doesn't diatomic only go up till 5 degrees of freedom?
No, it turns out, it turns out they can fight.
Because I remember it's transitional and then you get rotational and then
Right,
I guess it's vibrational last one.
Right. You probably learned this from chemistry maybe. This is rotational,
And then vibrational.
this is vibrational.
Okay, got it. Yeah, I did it.
Right.
That's just
You would think it's 1, but it's actually 2. For simple harmonic oscillation, one mechanical calculation shows that it's actually 2. Or not necessarily one mechanical, actually classical calculation also shows there's 2. Right. But that requires you to go into the whole full-blown discussion of statistical mechanics, which we're not doing.
One more thing about Maxwell that you think about till now. You said Maxwell thought there'd be 6 degrees.
Yes.
Because of spinning along the y-axis.
Yeah, because well, we have two atoms per molecule, right? One has 3, another has 3. Right, so it's 6. Classical mechanics shows that there's 6 degrees of freedom.
But under that reasoning, wouldn't we say for a monatomic there'd also be 6? Because it could move 3 ways but also spin 3 ways?
Yeah, I suppose you could know it that way. No, I've never thought about it. Yes. Right.
Okay.
No, if you think of it as a real ball, right, a real sphere, right, then yeah, sure, you can rotate and whatnot. Right. How come Maxwell never discussed that? I don't know. Right, he always assumed that monatomic means that 2 degrees of freedom, so meaning that the whole thing has an extension.
Okay. It made more sense if classically we thought there'd be 5 degrees of freedom.
Point space. You said it's a point space, so it
If
doesn't.
it's, yeah, you can do that also.
But that would lead you to think 5 halves rather than 6 halves. Because if they were points, then they would rotate this way and they could rotate that way, but they wouldn't be able to rotate that way.
Right,
Yes,
that's
that's
5½ right? But then there's also there's also 7½.
That one would have been predicted at all.
Right, and then he knew all these 3 things, right? He knew that depending on gases, because they didn't know anything about this transitional temperature, right? Depending on gases, sometimes they see something like that, sometimes they see something like this, sometimes they see something like that, right? And he got all confused, that's it, right? In 1860, he got all confused.
Does that only apply to gases, or does it work for solid?
In solid also there's what's called, techniques that I'll never get it. There is called the long petite. I don't know if this is this in the book?
I think they mentioned something about.
You mentioned it really briefly, but yeah.
Yes, so this is for the same thing here, right? If you have, but this requires more involved statistical mechanics calculation. If you do a classical stat math, right, for a solid, you can think of a solid as a lattice, right? And things can vibrate, right? So each atom can have 3 degrees of freedom, right? But since it's executing simple harmonic oscillation, right? So you have this is trumpet T. I don't think he did the calculation. I think Boltzmann did the calculation. But trumpet T did the experiment. So each atom has 3 degrees of freedom, X, Y, Z to vibrate. Okay. But from equipotential theorem, so I was lying a little bit. This is from statistical mechanics. For each kinetic energy, for simple harmonic oscillation, this 1/2 kT. This is 1/2 mv squared, right? But also for simple harmonic oscillation, you have 1/2 kx squared, right? This gives you another 1/2 kT. Right? That will give you exactly kT, right? Per atom, right? So the specific heat then becomes N K, right? Right? Just NK, right? Times 3, right? Because there's 3 directions. This is called the result to long T, right? So it's flat. CV, the function of temperature, is flat. 3, I guess chemists write it 3 bar, but you know, I'll stick with NK, 3 NK. Right? So your result shows it goes like this. And this is the problem that one of the problems in the homework. I assigned it to you. It should be a simple problem, but it turns out it's actually dq here. Right? At low enough temperature, it's dq. And this is solved first by Einstein. 1907. So, but the experiment was already there, right? Einstein was just showing that, well, if I applied Planck theory into metal, right? He can explain the discrepancy from that. Well, I want to solve one of the heat transfer problems. And this is also your homework assignment, by the way. So you don't have to do the homework if I just copy what I write here. What I miss it now. So if I have a piece of black body, right? This is the black body radiation. I'm not going to go into the detail of what a black body is, right? But, and I'm just using the formula they gave you in the book. By the way, did people go to the talk yesterday? Yeah. You might see what's there. The flux. I'm not going to talk about the flux. Yes, the flux of heat coming out from the black body, right? It's going to be sigma d to the 4 times the area, but this is the flux, let's call it the dq dt for simplicity. This black body has an area A, right? Then the heat, the radiation heat that is given off by this black body at temperature T is going to be proportional to sigma d to the power of 4, right? Times the area. And just to be precise, there is what's called the emissivity of the material. And for a black body, emissivity is 1. Okay? So the question is, I think this is the homework, right? Did I assign it in the homework? I have the sun. A temperature of 6,000 K, right, at the surface. At the surface is 6,000 K, somewhere inside is not. Right? And I have the Earth.
This is exactly what we're doing extra.
And it's in radiation constant at 1 minute. Right? And I want to analyze it. Okay? So the Earth is also, so this, you can consider the Earth and the Sun to be black body. It's probably not correct for the Earth, it's close to being correct for the Sun. Okay? The Earth has some temperature TE, right? This is the radius of the Sun, the radius of the Sun, this is the radius of the Earth. Okay? And the distance is 1 angstrom, right? No, not 1 angstrom. Okay, let's call it RSE. Okay. So what happened is, I want to cut. What happened is this is radiating and that's radiating, right? It's black body radiation. And at some point, at least not on the sun is not in equilibrium. The sun is a hot spot in space, right? But here, I can consider the Earth. The Earth is close to being in equilibrium, right? So it receives a flux from the sun, right? It gets energy from the sun, right? But it's also radiating energy out because it's a black body, right? And but you know, at whatever the temperature the Earth is, it's in equilibrium, right? The Earth is not getting hotter, it is getting hotter, but it's because of something else. But it's, you know, the Earth is pretty much about the same temperature, so it's in equilibrium with the radiation coming from the sun. And we want to calculate what is TE. I think that's the homework assignment, right? Okay. What time is it now?
54.
54. Yes, I can do it. So the heat, this is, you know what a dot is, yeah? Derivative with respect to time, right?
Yeah.
Okay. Then is equal to that, right? Sigma E of the sun to the power of 4th, right, times the area of the sun. What is the area of the sun?
4 pi r sun squared.
4 pi r sun squared, right? Okay, and the radiation given off by the Earth is given by
Sigma T or
Q Earth dt sigma T Earth power 4 area of the Earth, which is 4 pi RE squared. Right? So in equilibrium, these two are the same, right? Or is that not true? It's not true, right?
No.
No, it's not true because back to my story here, only this portion of the radiation will be Earth, right? The rest goes into outer space, right? So we want to calculate what is the portion that actually hits the Earth, right? The portion of QS that hits the Earth we'll talk about flux in the context of ENN, but you know, so we define what flux is and whatnot. But for now, we just have to look at the portion that, you know, just the solid angle that's subtend the disk of the Earth if you look at it from the sun, right? What is that equal to? So remember this?
Well, it's like
Is the area, so if you look at, if you're somewhere in, you know, at the center of the sun, right? You look out, right? This disk has an area of, quote-unquote area, but this area, projection of the area, right, that you get from the sun, right?
Pi RE squared over,
right? This is pi
over
RE squared, right?
all over,
Yeah.
Divided by
RSE squared.
4 pi r sin earth squared, right? Divided by the total area. That's total area.
Why
And
would
this calculate solid angle. This solid angle is just this area divided by the area of this whole sphere.
Why wouldn't you just use for the area of the Earth? Why wouldn't you use 1/2 pi r e squared? Because like half of the area is like on the other side. Right?
Oh no, but if you want to do that, it's actually 4 pi, right? Right. No, I'm actually just looking at it from this side, right? So I have to take into account the fact that it has a curvature,
Oh, okay.
right? So, but looking from the sun, right? If you look at it, it just looks like a point, right? Like a disc, and that disc has an area of pi r
So
squared.
where do you get that formula?
Oh, this is just the area. This is just the portion that hits the Earth. But the flux goes in all directions.
No, what I mean is.
It's a solid angle formula.
Oh,
Solid angle. I'm just calculating solid angle.
Okay.
Yes, this is correct. Right. So what is the solid angle? What is that solid angle? Right. It's given by like this ratio. Right. And this just it's become 1/4 r e to the square over r s e squared. So only this portion of that reaches the Earth, right? In equilibrium, then this times that 1/4 r e squared over pi r s e squared has to be equal to that, right? And if you put in all the number, you put 1 angstrom. I don't know what to get if you put 1 angstrom. You find that EE is going to be like roughly around 300 K, so it's not that bad. Right? But the temperature of the Earth is actually a smaller increase, right? Is what is exactly 0, around 0? You know the statistics and stuff.
Yeah, well, I don't know the exact values, but I know that it's better of an emitter than it is an absorber.
Oh, better emitter than an absorber.
Yeah, it only reflects more than it.
Okay. Right, yes.
So it would be lower.
Lower,
The TE would be lower.
lower than that, right, yes, okay. Right. Because, okay.
Would you have to divide by then like epsilon, then to find the actual value? Like
Oh, yes. Epsilon, well, we're assuming it's a black body.
But Earth isn't.
It is not, right? Yes, I think it's the point that you must make, right? And yes, sigma, you can find sigma. And if we are vicious, we can try to derive this. This derivation is not quantum mechanical. This derivation is actually classical. That's the most amazing thing, because the radiation process, right, if you want to look at the distribution, just like what you guys were seeing yesterday, right, that black body radiation is divided by Planck. But if you integrate that function, you get this result, and this can be derived, Boltzmann derived this. That's why this is called the sigma here is called Stefan Boltzmann constant. Right, Stefan did the experiment, Boltzmann did the theory. He's the student, he's the professor, he's the student.
He's handing out homework. Okay.